Thank you. So the next talk is by Phil Metzger from the University of Central Florida, and I think Phil is using his own laptop.
So while we're dealing with a logistical thing, let me just start talking for the sake of time. So I'm Phil Metzger. I co-founded a laboratory at NASA called the Swamp Works, where we develop space mining technologies. And for about 10 years, I've been trying to solve the problem of how do we economically start industry in space? What are the economic pathways to make that happen? And it's a difficult problem to solve because we require a significant investment at the beginning of space industry, and you're not going to get a significant payback until quite a ways down the road. And as a result, it's hard to attract investors, and it's also hard to get national governments to understand. Oops, I'm trying to find out where I saved this. It's hard to get national governments to understand the vision for why we need to do industry in space. It's hard to talk and do this at the same time.
Oh, take your time. And
So I'm looking for the RAS specialist discussion. I think I'm here. That doesn't look like the right title. Oh, it is. Okay. And then this is you right here. Correct?
Kingston, yes, that's right.
Okay. There we go. And I'll let you do this if you don't mind. Okay, so as I was saying, it's hard to get national governments to understand the value of doing space industry. Why as a civilization do we need to do this? And it's also hard to get financial investment commercially into this because we're looking at payback times 10, 20, 30 years down the road with a high risk. And that's not your typical profile for doing commercial investments. If I wanted to invest in space industry, it would not pay back in time for my retirement. And so personally, I'm not going to get a benefit from my retirement account investing in this in the long term. And so I've been trying to figure out how do we crack this nut. And so I'm going to present what I think is one possible strategy, drilling down to, yep, that's it. And I apologize about that again.
No worries.
Okay, so one strategy to solve this problem. And I'd like to thank Ian for putting this together. This is a wonderful meeting, and it's a great privilege to be here in London. So I'm going to talk about using ice for planetary surface propulsion, a strategic technology to initiate space industry. Starting at the biggest picture, with Nikolai Kardashev, the Russian physicist, he talked about different scales of civilization, and he said a type 1 civilization is one that uses the energy of an entire planet. A type 2 uses the energy of an entire star, and a type 3 uses the energy of an entire galaxy. That seems really fanciful. Why would we even think about such things? But if you look at the history of humanity, we've already made transitions from level of civilization to the next level that are comparable in scale even to this. So looking backwards, a type 0 civilization would be an entire continent, like say the Roman Empire, and the continents were bounded by the oceans, which at one time in human history were insurmountable barriers, and it would be crazy to think about the things we're doing today in civilization. Going back even further, civilization was founded in the river valleys where they had silt deposits with intensive labor agriculture. They could farm those deposits, and they spread cities throughout those river valleys, but those limits of the silt deposits were the limits of their world, and they were a barrier that were difficult to transcend. And it took technologies and new ways of organizing civilization to learn how to go beyond the limits of those worlds. And going further back then, we were hunter-gatherers. But when you go from one type of organization and civilization to the next, you're crossing a barrier that requires new technologies. And if you think, for example, how the Polynesians felt when the Europeans showed up in ships, coming from a part of the world that had technologies based on metallurgy, things that weren't possible in those islands, it was a culture shock. But what an even greater culture shock it would be today if they saw us show up with today's ships, container ships, where we cross the ocean. Like, for example, this mouse probably involves 6 or 7 ocean crossings to get the metal from South Africa, the petroleum from the Middle East, to refine the metal maybe in Japan, the petroleum maybe in New Orleans, to make the silicon chips maybe in Korea, to assemble the whole thing in China, and then to bring it across the ocean again and sell it for $15, a trivial cost. So we've transcended these barriers before, and we're good at it. We're a species that can do this. And so there have been several studies that have shown that initiating space industry will free humanity from the limitations of a single planet. And studies have shown that it's generally feasible through geometric growth of industry in space. We can have factories, build factories, and we can scale up very rapidly so that within this century, we could have a vastly larger type civilization. Right now, humans are leveraging in the West, we're leveraging our ability to produce goods and services by about 1,000 to 1. In the United States, it's 1,500 to 1 by using machines burning energy doing thermodynamic work 1,500 times faster than the muscles of all the laborers in the workforce. But if we went to space industry and grew at large, we could be 1,000,000 to 1 by the end of the century. And this would allow us to solve our global challenges. We have climate change, limits on water, energy problems, on and on. And I'd submit that all of these global challenges are symptoms of just one problem. It's not a coincidence. They're all happening at the same time. It's because of the most obvious thing. We've become a global civilization, and we're starting to push the limits of our planet. And therefore, the one really natural solution to all of these global challenges is to stop relying on one planet, to get over this barrier that we have begun to feel. And therefore, space robotic industry is the real key to solving them all. However, time is of the essence. If we're going to make a difference in time for all these problems, then we need to get space industry started. But because the barrier to civilization is a larger barrier than we've ever faced before, it's a hard one to solve. It's a hard one to get over. Now, the fact that we can solve these global challenges through space industry is really not obvious to non-specialists. And so politicians have no vision for this whatsoever. And if we want to try to lead the way through the commercial sector, then we need to create economically viable pathways, as I was saying a couple of minutes ago. So who are the customers for space industry? Well, we could support space science. We've heard a little bit about that this morning. Space agencies like NASA, however, aren't really committed to using space industry. And also a problem in terms of getting space industry started is that they're not going to do a lot of Mars missions in the current economic paradigm. And so they're not really a huge customer. We could use space tourism. We've heard a little bit about that. That's also probably a limited customer base. Maybe people like Elon Musk are going to start a colony on Mars, and they could use space industry to help supply their needs. I think one of the most strategic ones is supporting Earth's economy today by doing data and voice and video services from space. Boosting spacecraft from low Earth orbit to geosynchronous orbit requires upper stages, which require fuel. There was a study a couple of years ago at the International Space University. The study was called OASIS, and they looked into the possibility of providing data services, having them be our customer for space mining. And so they looked into what it would take to have a space tug that you would refuel in orbit using water. And they looked into the idea of a logistics node in low Earth orbit. But the logistics node was still pretty expensive. The idea was that you would get water, you would electrolyze it to hydrogen and oxygen, you would need cryocooling, you would need all the spacecraft structure, the radiator panels and solar panels. And it turned out that the investment, or the price to build this, would require an investment that probably commercial partners are not going to pay for. It would pay itself back in 20 or 30 years if you had 0-point financing. So this would be something that the government would need to lead. People have said, well, let's go to a simpler version of Cis-Lunar water economy. Maybe rather than electrolyzing water, are there some simpler first steps we can do? One idea that people have been talking about lately is getting water from small asteroids by bagging, heating them, and then liquefying the vapor. And by the way, I want to mention, I agree with Paul Sputis, the moon is the solution. If you really want to go large-scale industry, I don't think near-Earth asteroids are going to scale up large enough. I think Jim Caravallo might talk a little bit about this later, how the moon can help solve global challenges. But as a simple first step, we could use near-Earth asteroids. Don't electrolyze the water and just use it as steam propulsion directly. It's easier to store water in orbit than to store hydrogen and oxygen. You don't need the equipment for electrolysis, the cryocooling. The ISP, which is the specific impulse of a propellant, is 160 seconds for steam propulsion. That's not as good as the 450 seconds you get from hydrogen and oxygen, but it's actually not bad for such a simple system. And then if we could get this started, we could develop more complex infrastructure over time. But we can go even simpler than that. So I think this is one of the simplest first steps we can do that's along a strategic pathway to starting industry in space. And that would be to do planetary exploration using in situ water. All of the infrastructure for this quote-unquote water economy would be on board a single spacecraft. The mining would be on board the spacecraft, the propellant depot with the cryocooling or the chilling to capture the vapor would be on board the spacecraft, and then the heating and propulsion would also be, so the customer would be on board the same spacecraft. A planetary mission would therefore be a small-scale model of a future cis-lunar water economy. And this would provide us the opportunity to develop critical technologies and to provide a proof of viability for investors. So I think doing simple steps like this might lead the way in helping start something in cis-lunar space. So a very simple spacecraft would look something like this. There would be a mining system, which would be a mechanism to extract or isolate planetary surface material, heater to liberate the volatiles. Then you would have a propellant management system, a tank with chillers to liquefy the vapor, a valve to keep it from flowing backwards through the system when you're heating for propulsion. You would then heat it, bring it to a supercritical state. You would then have a throttleable valve to vent it through the nozzle, converging, diverging nozzle. You're venting into vacuum, and therefore you're always below the critical pressure, and so you always get supersonic flow, which gives you the 160 seconds of ISP. And you need an electrical system or a power system. So I have a contract right now. I'm subcontractor to Honeybee Robotics on a project we call WINE, The World Is Not Enough, developing small spacecraft, CubeSats, that refuel in flight. And Honeybee Robotics has developed several different mining mechanisms. I'm not going to show the pictures of them yet. This was a phase 1 project, and we're just wrapping it up and getting ready to write our phase 2 proposal. But they developed several different mining systems that would work on a CubeSat as well as on a larger spacecraft. Here's a picture of a larger spacecraft that they've proposed. This is an asteroid water extracting system where there are drills on the legs. They bring drill cores up into the legs, which then heat and extract the water, which gets piped back to the cooling tank on the central part of the lander. So we've developed asteroid simulant. I've done this in collaboration with Deep Space Industries. We've crushed various minerals and mixed them in the right proportions to represent different kinds of meteorites. And we've created these very dry, dusty powders that have the right mineralogy to represent different classes of asteroids. And this is Steve Covey on the right with the meteorite that we've made. We've solidified it with vacuum baking to create a competent rock. So using this bone-dry simulant, which has hydrogen locked up in the minerals, in the clay minerals for a carbonaceous asteroid, Honeybee Robotics has used their small spacecraft mining technologies, and we've extracted this water, beautiful, clean water. So we've shown it's feasible. A power system on a small spacecraft, there's 2 different ways to do it. You could have just-in-time heating, where the water is heated as it vents through the rocket nozzle. This overcomes the problem of the high heat of vaporization as the water goes into the vapor state from liquid, but it requires a huge power, a huge rate of energy expenditure. You could use solar concentrators. for small spacecraft that would require deployment mechanisms. We're going to look into this in phase 2 of the project, but for now we're looking at in-tank heating. It's the simplest way to do it. You can have a small power source, you heat the water in the tank, you just need to have enough thermal insulation, you get it up to maximum temperature, close to the critical point, and then you vent it. You could use solar, RTG, or another nuclear decay source. So the way this works is you're heating along the steam saturation curve inside this tank. You begin at some cold point, you've been liquefying the vapor, you close off the valve, you begin heating it, adding entropy to the system, you get up near the critical point, and then you begin to vent it out through the nozzle. As it vents, it carries away enthalpy, the water remaining in the tank comes back down the saturation curve, and I would love to show you how we solve some new equations to be able to do this in spreadsheet form. It's a very non-ideal gas, but we've come up with a very rigorous solution that works in a spreadsheet for doing trade studies. So the first case I'm going to show you is for a CubeSat. This, if you're not familiar with a CubeSat, it's a 10 centimeter by 10 centimeter by 10 centimeter spacecraft architecture. They're stackable. People will typically go up to 6 units in a 2x3 array of these little cubes. And so looking at a 6U CubeSat in lunar gravity, if 3U of the internal volume is available for water storage, and you can use conformal coating inside and use all the available space if necessary, 10 centimeter nozzle diameter, heating the water to 39 Kelvin less than the critical point, which gives us very doable pressures inside the storage tank. Doing this modeling of the water venting out through the nozzle, you get a good thrust for about a second, and then it drops off over the next 9 seconds. It turns out that you can only use half the water in your tank at a time using this approach. By the time you've vented half the water, the other half freezes solid in the tank. So that might make you think it's not a very good system. But for simplicity, you actually still do get really good performance. Looking at the performance of the water going out the nozzle, the temperature drops a little bit, the exit density drops from 1 to 10 seconds, which gives you a drop off in thrust. But the specific impulse is about 160. There's a cumulative specific impulse, which is stays around 160 for the entire thrust event. In lunar gravity, you've got gravity drag, and so the effective specific impulse drops from 1 to 10 seconds as the thrust becomes a ever smaller fraction of the vehicle weight. And so the real issue here are hopping distances. How far can you go with this sort of a very simple in situ system of propulsion? It turns out that the throat diameter is a very sensitive determinant for the amount of acceleration your spacecraft gets. And if you want to limit it to a reasonable acceleration, something less than 10 G, you only get a very modest drop in your hopping distance overall. We've also looked at the exit diameter of your nozzle. The larger the nozzle, the more weight you've got on your vehicle. And so there's an optimum point. For this 6U CubeSat, it looks like we can hop about 2.5 kilometers on a single tank of water, which is really good. The first hop I mentioned uses 50% of the propellant, leaving the other 50%. You heat again, and then you get a second hop, which uses another 30%, leaving 20%, and the third hop uses 15%. At some point, you mine and refill your tank. It also depends on how hot you make your tank before you hop. If you get close to the critical point, then you get very high pressures. By dropping down just 20 or 30 Kelvin from the critical point, you get a dramatic reduction in tank pressure for only a very small loss of performance. And then let's look at how far you can hop versus your propellant quantity. For a 6U CubeSat, if you're using 3 or 4 units of the volume for water, you can hop about 2 to 6 kilometers. We also looked at large spacecraft like a Phoenix lander, Mars lander scale spacecraft, and using reasonable amounts of water in the tank, 40 to 80 kilograms of water, you can hop 5 to 20 kilometers with this architecture. So again, very practical to use this on a planetary mission. And so finally, looking at different bodies in the solar system. For a 6U CubeSat on Mars or Mercury, the ice at the pole of Mercury, you could hop close to 1 kilometer. For the moon, there's an energy problem if you go down in the permanently shadowed craters. But just for grins, if you look at hopping on the moon with this sort of a spacecraft, you could go a couple of kilometers. Europa or Titan, exploring the surface of those bodies, you could hop a couple kilometers with each tank full. Triton, Pluto, Titania, Oberon, you're getting up in the multiple kilometers, 10 kilometers range. And Ceres, if we can get water, it's carbonaceous, and if we can extract water from the minerals, then we're talking about 20 kilometers of hopping distance. Likewise, a Phoenix lander scale spacecraft can hop about a kilometer. Well, it's really the same distances as a 6U spacecraft. So again, very feasible to do this in space. So I want to close with this. Humanity does not really have a resource problem. We're feeling this crunching here on planet Earth with energy and water and other things. But what we really have is an imagination problem. And we've got to get the politicians to understand that it is true that it's really not economically viable to do big space industry and make it a profit doing it if you evaluate it in the current paradigm. But what we're talking about is changing the paradigm. If you put robotics in space, harvesting resources, robots building robots, that's a paradigm shift. And because of the advances in robotics, this is coming, and it will be possible to complete this paradigm revolution by the end of this century. So what we have is not a resource problem. It's really just an imagination problem, getting people to see that this is viable. And so I like to tell everybody we need to think outside the sphere. So thank you.
Thank you, Phil. And we also have time for questions after this talk. So there's a gentleman at the back.
Hi, two questions. First one is, you're looking at baselining this for a CubeSat. Have you compared the performance to the Hydros unit from Tethers Unlimited, which I believe has already undergone a flight test? Also, for these hopping maneuvers, why not just have a coiled spring and recoil it every time? Oh, no, and third, sorry. Have you factored in the guidance for these hopping maneuvers, and are you using the thrust for the landing as well?
Okay, so I'm not familiar with the Hydros, but this was a phase 1 study, which was just a 1-year small amount of funding. And so we haven't looked at all of the spacecraft systems, and it was a feasibility study. So we looked at 2 of the major components, which was the mining part, and then we've also looked at the water propulsion part to make sure that both of those, what we thought were the 2 biggest challenges, would be feasible. And they both appear to be very feasible. So I'm sorry I can't comment about the Hydros. About the spring, the answer to that also answers your third question. Yes, we're using the water for landing as well as for launching, and so a spring won't provide that. And I failed to mention that for the CubeSat, those were round-trip hopping distances. So you're saving enough hop to come back. So you launch, and land again. The idea there is that for a CubeSat, you may be operating from a larger spacecraft. And so you could have a large spacecraft that sends out the CubeSats as drones to collect samples and bring them back and work an area. Then the mothership could then hop to a new location. So the mothership might provide the mining for the CubeSats instead of having them do it themselves. I hope that answered the question. Oh, and as far as the other spacecraft systems, guidance and such, we're right now doing the overall design of the system. And we're looking for a CubeSat, we're looking at using off-the-shelf components because these things have mostly been developed already.
Thank you. Well, there, I think.
Oh, okay. It was a very general question. It's what is the information that you most need from scientists?
The information that we need from scientists. Okay, so I'm a planetary scientist myself, and I tell young students that I think they're going to be the rock stars of the next century, because if we are successful at putting industry in space, then we're going from being a species with one world to a species that has many planets. In fact, I think the meaning of the word world will change to be solar system. So I think that we need scientists to understand all of these environments. And so there's a huge amount of work. Like, for example, just the moon alone, we don't really understand the state of the soil, where the ice is, the physical state of the water at the poles of the moon. We need to understand the plasma environment for spacecraft operating there. We've got a whole solar system of science that needs to be done to learn how to do civilization on all these bodies.
But I think we have time for another question because the next speaker, sorry, I thought you moved you. We'll have one more question if anyone's got one. Okay, thanks.
Hiya. Given you were saying about the history of our moving from the silt plains to another, broadening our horizons, given we've done that so many times, what is it about human nature that makes it so hard for us to say, well, let's just do the same again but better? What's holding us back?
Okay, so I'm not an economist, and I can't give any rigorous answer to that, but all the economists that I know don't have the vision for going into space, and they like to tell us how this is not economically feasible. And whenever I've been in a meeting with economists, they're always the naysayers. I think part of the issue is that as long as we were spreading industry on the surface of the Earth, we were spreading out. It was always a more gradual change. Oh, I think I can partially answer it this way. Everywhere we've gone with civilization so far, our bodies were more or less adapted to that environment. This time, we're trying to go away from our ecosphere to a place where, as far as we know, there is no life. And so a way to look at it is this industry that we're going to put in space is going to be an artificial ecosphere. We're creating an artificial life that uses local resources to create a metabolism, to reproduce. And we're creating a designer ecosphere that's adapted to the absence of liquid water. We've never had to do that before, and so it's a new place we're going. Okay. Well, thank you.
Thank you. Thanks for